asset price process. Okay, so let's say what we have is this thing is correct. WT equal to the expectation MT plus 1 WT plus 1. Let's say this is true, and let's say we choose WT to be the dividend reinvested asset price process. Okay, and let's say it is called S. Okay, so this is true. Okay, let's say this is the dividend reinvested asset price process for assets I. Okay, so we buy assets I at the beginning of time, and we get some dividend from assets I. Then we buy more of this assets I using only the dividend. Okay, so this is the dividend reinvested asset price process. And what do we get? We get MT equal the conditional expectation. We have MT plus 1. We have SI T plus 1 divided by SIT. So what is this? What is the value of this dividend reinvested assets price process? At the beginning of time t, we have SIT, so we buy SIT of it. And after one period, what do we get? So let's say at the beginning we buy PIT of it. Okay, for the first period we buy PIT of it. And one period later, what do we get? One period later, we get the IT plus 1 and the dividend, right? Right? So this is what we get. And what is this ratio? This ratio is just the total return. Okay? So this ratio is just the return on the ith asset. Okay, so this equation becomes MT equal conditional expectation MT plus 1 times asset return. Okay, and this is the definition of SDF process. Okay, and this is just the definition of SDF process. So once again, the other direction, we want to prove that if this equation is true, if MWT is a martingale for any self-financing wealth process, then M is an SDF process. Okay, so how do we prove it? We just choose a particular self-financing wealth process. We choose the dividend reinvested price process. Okay, then this equation is true by assumption, and we divide SIT from both sides, and we know that since this is just a dividend reinvested price process, this ratio is just the return, total return on the asset I. Okay, so this equation becomes MT equal to the conditional expectation of MT plus 1 times our IT plus 1. And it is true for any I, because for any asset, this SIT is a self-financing wealth process. Okay, so this is the definition of SDF process. Okay, so we can derive from this equation to the definition of SDF process. So we have finished the proof. Okay. Okay, it's just some remarks. If W is a self-financing wealth process and M is an SDF process, then MT can be used as an SDF for the period of time starting at day 0 and ending at day t. This is what I just said. What is MT? MT is an SDF, okay, but it is not discounting for one period of time. It is discounting for t period of time. So if we have a M capital T, then we are pricing a self-financing wealth process for a capital T period of time, okay? And if we want something in middle, so we want a WT, W small t, then we can use M capital T divided by M small t to discount WT, okay? Okay. So just now we talked about the self-financing wealth process and its relation with the SDF. But usually we don't have self-financing wealth process because we need consumption, okay, and we have income. So what happens if we have income and if we want to do some consumption? Then we have this equation. This equation is actually just a budget constraint. Okay, on the left-hand side, what do we have? We have a WT. Let's say now it is time t. So we have WT, the initial wealth, and we have a set of income. So from time t plus 1 on, up to capital T, we have some income for each period of time. The income can be random. Okay, so we have to price them. How do we price YS? How do we price some future income? We price it with the SDF process, okay? And we want to discount them back to time t, so we use MS over MT to discount the YS, okay? So on the left-hand side, it is the total value, it is the total worth of this person, okay? It is the total discounted value of all his future income and his wealth. On the right-hand side, what do we have? We have consumption and we have wealth. Okay, consumption is a function of the income and his portfolio return. Okay, so consumption is also random. So to price consumption, again we have to use this SDF process. So this is the total value of consumption. Okay, everything that this person is consuming, and this is the terminal wealth. Okay, so how much money is left on the end of the road, okay? So usually we would just set WT, W capital T as C capital T. So on the last day when he's dying, and he know, because when we know what capital T is, so on the last day he will consume everything. Then on the right-hand side we have the total value of consumption, okay? So these two, the left-hand side and the right-hand side should be the same. Okay, because on the left-hand side, it is the total net worth of this person. That's the total amount of value he has at time t. Okay, and when he plans on his consumption process, the worth of his total consumption should be the same. Okay, so he cannot overspend, and he would not leave anything. Okay, so this is a budget constraint, and we can show that this is true using the intertemporal budget constraint. Okay, so what is the budget constraint we have at the beginning of today's class? So this is the intertemporal budget constraint. Okay, and we will show that the overall budget constraint can be implied by this intertemporal budget constraint. Okay, so we go back. So we want to prove that this is true for any capital T. So we will prove for any small t. So we will prove it by induction. Okay. First of all, so we have a capital T here. It is easy to see that this equation is true when small t is equal to to capital T. Okay, because this income starts at t plus 1, so it goes away. There's no income anymore. And this consumption part goes up to t minus 1. Okay, so there's no consumption as well if small t is capital T. Okay, so on the left hand side we have W capital T. On the right hand side we have W capital T, and we have M capital T divided by M capital T, so there's nothing left. And conditional on capital T information, W capital T is non-random. Okay, so on the left hand side we have W capital T, on the right hand side we have W capital T. Okay, so it is correct, it is true in when small t is equal to capital T. So we prove the other t for by induction. So how do we prove by induction? We assume that it is true for some t, and then we prove that given that any t or a t minus 1 would also be true. Okay, because we already know that capital T, this is true. So if we assume that it is true for t plus 1, then we prove that it is also true for t. Then we prove this everything. Okay. So suppose this is true for t plus 1. And what is the intertemporal budget constraint? Okay, assume that it is true for tau plus 1. So we don't mix up notation. So this is the budget constraint. So tau plus 1. We have some income. Okay, we have some investment. The amount of investment is W tau minus C tau. Okay, we are investing in some portfolio. Okay, and we get some return. This is our intertemporal budget constraint. Okay. So let's say we want to price this W tau plus 1. Okay. So what we do, we multiply a M tau plus 1. We multiply it and we take the conditional expectation. Then we know the value of W tau plus 1 at time t tau. Okay. So we do this. To the right hand side we have expectation tau, M tau plus 1, Y tau plus 1. So we don't know what it is. We have these two things, or these three things, these three terms. They have subscript tau, and they are tau t, date tau. And the date tau information, they are known already. Okay? So when we take the conditional expectation, we can take them out of the expectation operator. Okay, so we get a W tau, we get a C tau, we get a pi tau, and then we get a conditional expectation. Okay, and also the M. Okay, we have the M tau plus 1, and then we have the R tau plus 1. Okay. So what is this guy? What is this guy? We are pricing the return at time tau plus 1 using M tau plus 1 conditional on time tau information. Okay, so by the definition of SDF process, this becomes M tau. Okay, and we have n of it, so M tau times 1. Okay, and we have a pi tau here. It is just some portfolio, and some portfolio times 1 becomes 1. Okay, so on the right hand side, what do we have? We have conditional expectation. We have M tau plus 1, Y tau plus 1. This is something that we don't know what it is. We have the amount of money that we put, that we left for investment, and then we have an M tau. Okay. Okay, so this is the value of W tau plus 1 conditional on time tau information. Now suppose that this equation is correct, okay, at time tau plus 1. Then what do we get? So we get a W tau plus 1 plus the summing from tau plus 2 up to capital T of your income, and then this is summing from tau plus 1 up to T minus 1, and then we have the terminal wealth. Okay, and let's say we multiply an m tau plus 1 everywhere. Okay, so this is the intertemporal budget constraint, and now we use that equation. Okay, we multiply an m tau plus 1 everywhere. So on the left hand side we have m tau plus 1, we have W tau plus 1, okay, and then we just copy everything. Okay, we're summing S from tau plus 2 from tau plus 2 up to capital T. We have the conditional expectation condition on tau plus 1 information. Okay, so this is the equation, that equation at tau plus 1. We assume that it is true. Okay, and then we have this ms, we have this ys. Okay, this is the left hand side. The right hand side we have summation S from tau plus 1 up to T minus 1. We have conditional expectation, conditional on time tau plus 1 information. We have the ms, we have the cs, and then we have the conditional expectation of m capital T, W capital T. Okay, so I'm just copying that equation with time tau plus 1. Okay. Okay. So here we have an equation of the conditional expectation of m tau plus 1 and W tau plus 1. So here we also want to write an equation of m tau plus 1, W tau plus 1. So we just put this sum of the income to the right hand side. Okay, so what do we get? We have a plus here and we have a minus here. Okay, so this is just the same equation there, but we put this summation of the y's to the right hand side. Okay. So we have two equations about m tau plus 1, W tau plus 1. What do we do now? We just take the conditional expectation at time tau, okay, to this equation. Okay, then on the left hand side we will have conditional expectation of m tau plus 1, W tau plus 1, and we have conditional expectation m tau plus 1, W tau plus 1 here. Okay, so after we take conditional expectation, then we can just equate these two equations. Okay, so we take conditional expectation. Then on the right hand side, what do we have? So expectation is linear. Okay, so we don't change this. And what is the conditional expectation? Okay, so we have a conditional expectation of another conditional expectation of some random variable. Now here it is just ms, ys. So we have a conditional expectation of another conditional expectation. Okay? So what is this expectation? What is this expectation? So we can just apply the law of iterated expectation. Why? Because time tau plus 1 information is larger than the time tau information. Okay? So time tau information is a subset of time tau plus 1 information. So we are conditioning on more information, okay, in our expectation here. Okay? And then we are taking another expectation that's conditioned on less information. Okay? So this would just be the conditional expectation, but now we are not conditioning on time tau information, time tau plus 1 information. We are conditioning on time tau information. Okay? But the things inside are the same, so we still have ms, we still have ys. Okay? And we still have s equal tau plus 1, t minus 1. Again, we take conditional expectation on this conditional expectation, and what we get is time tau conditional expectation. We have ms, we have cs, we have conditional expectation at time tau information, mt, wt. Okay? And we know that these summations have to be the same as this thing. Okay, so we have conditional expectation of m tau plus 1, w tau plus 1, conditional on time tau information, which is this long summation. With the intertemporal budget constraint, we know that the conditional expectation of m tau plus 1, w tau plus 1, conditional on time tau information has this form. So these two must be the same. Okay, so we can just equate them. Now we know that this and these are the same, so what do we get? Here we have the summation of conditional expectation of ms, ys. Here we have the conditional expectation of m tau plus 1, y tau plus 1. So we can group them together. Okay, here we are summing from tau plus 2 to capital T. Here we have a tau plus 1. So we put this term to the left-hand side. Okay, and then they can join together, so they become the summation s summing from tau plus 1 now. Okay, so it is summing from tau plus 1 up to capital T. Okay, and then we have this conditional expectation ms, ys. Yeah. On the left-hand side, we have a w tau, m tau. Okay, we just leave it. We just leave it here because we don't have the because we don't have random variable on the right-hand side. Okay. Yeah. So we have an m tau, w tau. On the left-hand side, we have a c tau, m tau. On the right-hand side, we have conditional expectation of ms, cs. And conditional on time tau information, what is m tau, c tau? What is the conditional expectation of m tau, c tau, conditional on time tau information? So given tau, these two are just constant, right? So we can treat them as constant, so it becomes m tau, c tau, okay? Which means that here we have m tau, c tau, we can write it as a conditional expectation of m tau theta. Okay, and we can put this minus to the right hand side, so we can take this thing to here. Okay, so we can merge them. So on the right hand side, we have the summation. Now we start at m tau theta. Okay, so we are starting as from s equal tau up to t minus 1. Okay, and what we have conditional expectation, conditional on time tau information. We have ms, we have cs. Okay, and we still have this last term. Okay, we have conditional expectation. We have m capital T, w capital T. Okay, so this is what we get by equating these two equations. Okay, and what is this? If we now divide the m tau from both sides, okay, so we divide, then we don't have m tau here, then we have a m tau here, then we have an m tau here, and we have an m tau here. Okay, so this becomes that equation. Okay, so we have w tau, so we have w tau plus the summation s summing from tau plus 1 up to t, conditional expectation. We have ms over m tau, we have ys. On the right hand side, we have summation s from tau to t minus 1, conditional expectation, ms over m tau times cs, conditional expectation, mt over m tau times wt. Okay, so we have that equation. Okay, so we finished the proof. Okay, so what are we doing here? We want to prove that this equation is true by induction. Okay, and we start with capital T. We know that capital T, at capital T, this equation is correct. Okay, so we assume that it is also correct for some tau plus 1. Okay, so we assume that this equation is correct at time tau plus 1. Okay, so we get this equation. And now here on the left hand side, we have a m tau plus 1, w tau plus 1. We know that we also have the same expression in our intertemporal budget constraint. Okay, so from our intertemporal budget constraints, we have this equation. So these two are the same thing. So we equate these two equations, and then we find that this budget constraint is correct at time tau. Okay, so we know that it is true at time capital T. We assume it is true at time tau plus 1, and we prove that it is true at time tau. Okay, then it means that it is true for any tau, okay, or for any t, by the principle of mathematical induction. Okay, so we prove this proposition. What does this proposition says? It said that the total net worth, or it says that the total value of consumptions has to be the same as the total net worth of an investor. Okay. Okay, so any questions for that? Okay, if there's no question, then we can now look at the relation between the market and the SDF. Okay, so in the last chapter we talked about the relation between SDF and arbitrage law of one price in complete market. Okay, so if law of one price holds, then there exists an SDF, and the other way around is true, and no arbitrage condition means the existence of a positive SDF. Complete market means the SDF is unique. Okay? And here we have something similar. Now we have a dynamic model, so the arbitrage has a slightly different definition. Okay, so what is an arbitrage opportunity? An arbitrage opportunity for a finite horizon T is a self-financing wealth process. Okay, so it is self-financing. We do not add in any extra funding, such that either say W0 is negative. Okay, so we get some upfront funding, but we do not have to pay. Okay, so W capital T is positive with probability 1. We don't care what it has to go through in the middle. Okay, but if W capital T is positive with probability 1 or non-negative with probability 1, then we can just buy or just sell this W. Okay, so we buy this W, meaning that we get some money upfront, and we hold this asset, and then we follow the strategy of this self-financing wealth process, and after some time at capital T, we can sell it. Okay, and WT is non-negative, so we can sell it without having to pay. Okay, that means that I get something upfront, and then I don't lose anything. Okay, so I have some free cash. The second, W0 is 0, so it is free, and it is non-negative with probability 1, and with positive